Welcome to the LÜTZE 360-degree video blog. Today we're diving deeper into the topic of demand-oriented cooling solutions for control cabinets. However, this time we want to explore the practical side of things. But first, hello Daniel, and welcome back to part 2. It's great to have you here again. Hello Michael, thank you for having me. For those who missed the last episode, let's start with a few words about you, Daniel. Sure, I'd be happy to introduce myself. I'm Daniel Haag. I'm a doctoral student at the Institute of Building Energy, Thermal Engineering and Energy Storage at the University of Stuttgart, specialising in building energy efficiency, thermodynamics and energy storage. Specifically, my focus is on electronics, cooling and the thermodynamics within control cabinets. Thank you. Let's dive right into today's question. Why is thermodynamics in control cabinet climate control so complex? We know there are numerous influencing factors and conditions, and that's what we'll explore today. Ultimately, we'll aim to understand why predicting temperature changes within control cabinets is so challenging. When it comes to weather, we can rely on forecasts a day in advance. So why isn't it as straightforward in control cabinets? That's a great starting point, and it almost calls the science into question. It's a criticism we have to accept. In principle, weather forecasts and control cabinet simulations are based on the same underlying physics, involving flow simulations. But the critical factor is the operating conditions. It's about what data we feed into our model. In other words, a model's prediction is only as good as the quality of its input data. In the case of control cabinet climate control, the most crucial factor is power loss. I believe you've had some practical experience with how this plays out, Michael. Indeed I have. Unfortunately, practice often deviates from theory. But why are these operating conditions so uncertain, and how can we interpret them better? To explain briefly, let's look at how we perform a control cabinet analysis. Typically, we receive a bill of materials for the cabinet. However, this list doesn't reveal how the individual components are arranged inside. There are internal company guidelines that often conflict with thermodynamic principles or best practices. So, having a specific component in the cabinet doesn't necessarily mean that it was calculated correctly. It's essential to know where each component is positioned within the space. And the most critical factor is the system's load, which is the power loss it generates. For reference, I have an illustration. It shows two diagrams, cross-sections of our flow simulation. On the left, you see the simulation with 100% potential power loss, which simply sums up manufacturer-provided power loss data. Here's where we encountered a major disappointment from a scientific perspective. We conducted practical measurements on the same cabinet alongside you. We noticed significant discrepancies between our calculations and the actual measurements. These discrepancies were clearly attributed to the fact that the power loss in the cabinet was much lower than expected. Subsequently, using the air temp calculation model we developed together, we reduced the power loss by adjusting the simultaneity factor until we achieved the best possible match between the measurements and calculations. The conclusion was that, compared to nominal operation, only 40% of the power loss was actually present in the cabinet. So, out of the initial 500 watts we assumed, only 200 watts were actually inside the cabinet, which is a substantial difference. In this case, the calculation model wasn't flawed, it was the initial input data that was incorrect. Therefore, it's crucial to recognize that individual analysis is essential, not least because you never know how each component behaves during cabinet operation. Absolutely. I believe that's the only way to dispel certain safety concerns. Operational safety and resource conservation don't have to be mutually exclusive. To reconcile them, we need a norm-compliant calculation, and it must be validated. In scientific terms, validation means verifying everything, recalculating, ensuring the model computes accurately, validating it against measurement data, and then calibrating the input data through comparison. I'm convinced this is crucial for both sides, for us in academia and for you in practice. It's the only way to build genuine trust. You've brought a second diagram from the measurement, haven't you? It shows the advantages of using an air blower fan. The first diagram, with many red areas, was initially shocking. What impact does the air blower have here? Yes, that's absolutely correct. The first diagram was shocking. Normally, we would have said that we definitely need a cooling device in that area. However, by calculating according to actual needs, we now have a lower power loss in the system. As a result, we can use an air blower fan to optimize the climate. This mixes the air layers at the top and bottom, achieving excellent results. In this diagram, you can see the temperature over a multi-hour measurement interval. The purple and green curves at the beginning represent temperatures at the top and bottom of the cabinet. Initially, they diverge as the cabinet heats up, resulting in some temperature spread. Eventually, a signal from one of the 3 installed PT100 sensors triggers the air blower fan. Within less than 10 seconds, we see the 2 temperature levels converge. This establishes a moderate temperature range well within acceptable limits. In this case, simply by designing for actual needs and installing the air blower, we were able to optimize the cabinet's climate very easily. Yes, you can clearly see that happening. The beauty of this approach is that it provides a sustainable solution. Thanks to a homogeneous cabinet climate, cooling is only used when necessary. It's essential to realize that individual analysis is key. Planning for high cooling power that isn't needed in the end doesn't make sense. These measurements are significant for us as well as for you, from a scientific perspective, to gauge how far theory is from practice. And, equally important, when customers see that their system operates at a much lower power or temperature range than anticipated, it's a significant benefit. So, thank you for sharing your insights. You're welcome, and thank you for having me. We look forward to more measurements. We're confident that we can show many users the optimization potential in their control cabinets. And I'm also looking forward to our next LÜTZE 360-degree video blog. Thank you.